All right, so by now you should have solved this example through Blackboard, and just give it your best shot, and then we're going to talk about it now. So remember, a Pareto efficient allocation is an allocation in which you cannot make somebody better off without making somebody worse off. Okay, so we have two agents. We have Stankonia, we have Riggedy Row, and each has a different action, Hawk and Dove or Hawk and Dove, and these are their payouts, where this is Stankonia's payout, this is Riggedy Row's payout, and it doesn't matter if you forget which order is which. In every test, I don't expect you to memorize the layout of the what's called the normal form of the game. I don't expect you to memorize the layout of this. I want you to understand what it means to be Pareto efficient in this case. Okay. So we have 4 different outcomes. Okay, and I want to see which outcomes can I make somebody better off without making somebody worse off. If I can successfully make Stankonia better off without harming Riggedy Row, then I can definitively say that an allocation is not Pareto efficient. Okay, so in order for something to be Pareto efficient, I need to take away from Stankonia to give to Riggedy Row, or to make Riggedy Row better, or vice versa. Okay. So if I want to say definitively that something is Pareto efficient, like if I wanted to say that this point, Hawk is Pareto efficient, what I would need to say is that if I go to Hawk Dove, or I go to Dove Hawk, or I go to Dove Dove, I cannot make Stankonia better off unless I take from Riggedy Row, or I cannot make Riggedy Row better off unless I take from Stankonia. So I need to eliminate all the cases in order to say definitively that Hawk is Pareto efficient. Okay, so let me show you exactly what I'm talking about. We'll do 2 examples now. Okay, so at Hawk, can I increase Stankonia's payout? Yes, this one increases Stankonia's payout, this one increases Stankonia's payout, this one increases Stankonia's payout. So all 3 allocations are better for Stankonia. And now I want to say, is there a way to increase Riggedy Row's payout in any of these 3 allocations? So if I go to this allocation, it increases Riggedy Row's payout. So I've already found one allocation in which I make Stankonia better off without harming Riggedy Row. So this cannot be Pareto efficient. All right. What about Dove Hawk? So if I go from Dove Hawk, this one here. Okay, so if I go from Dove Hawk to Dove Dove, I do increase Stankonia's payout. Okay, but if I go from Dove Hawk to Dove Dove, I decrease Riggedy Row's payout. So in order to make Stankonia better, here, going from here to here, I have to take from Riggedy Row. Okay, so I can't yet say this is not Pareto efficient. So far, it meets the criteria. But what about here to here? So if I go from here to here, I am increasing Stankonia's payout, but I am decreasing Riggedy Row's payout. So there are no allocations in which I can make Stankonia better off without taking from Riggedy Row. And there are no allocations in which I can make Riggedy Row better off without taking from Stankonia. So this is Pareto efficient, 0, 10. Okay. For the same exact reason, this one will be Pareto efficient. Okay, 10, 0. If I go from Dove Hawk to Hawk Dove, I decrease Stankonia's payout, and I decrease Stankonia's payout here. So this one has to be Pareto efficient too, because there's no allocation where I don't decrease Stankonia's payout. So in order to make Riggedy Row better off, I would need to take from Stankonia. Okay. What about here? Dove Dove over here. here. So if I move from Dove Dove to Hawk Dove, I make Stankonia worse off in order to benefit Riggedy Row. So I can't yet eliminate this. This looks pretty good so far. It meets the criteria. What about from here to here? So from here to here, I decrease Riggedy Row's payout in order to make Stankonia better off. So there are no allocations in which I can make Stankonia better unless I take away from Riggedy Row, and there's no allocation I can make Riggedy Row better unless I take from Stankonia. So all 3 of these allocations are Pareto efficient. Okay. In short, dove, because both players cannot do better than 5 without taking away from another player. Stankonia playing hawk and Riggedy Row playing dove. That's this one here. Is Pareto efficient because although you can make Riggedy Row better off with dove, this would make Stankonia worse off. Okay. And the same thing over here. Okay. Now I modified the payouts a little bit. So before this is 0, 10, and 10, 0. Now it's 26 and 520. So what's Pareto efficient now? Okay, so this one is still Pareto inefficient because I can make Stankonia better by going from negative 0.5 to 5 without harming Riggedy Row. Riggedy Row increases his utility too. Okay, what about here? What about, sorry, dove hawk? Okay, if I'm at dove hawk and I go to dove, I am not increasing Stankonia's payout. Stankonia does the same. Riggedy Row does worse, so I can't eliminate this yet. What if I go to hawk dove? So then I'd increase Stankonia's payout, but I would decrease Riggedy Row's payout. So this one looks good to me. Okay. What about going from what about this one here? Dove. If I go from dove to hawk dove, if I go from here to here, basically, I increase Stankonia's payout. I also increase Riggedy Row's payout. So I can make Stankonia better without harming Riggedy Row. I can make both of them better, in fact. Okay, so this one cannot be Pareto efficient anymore. Okay, so even though it's Pareto efficient here, because this is now greater than equal to 5, this is no longer Pareto efficient. Okay. Same thing here. This one here is now greater than equal to 5 as well. Okay. And then what about this one, hawk dove? If I want to make Stankonia, or if I want to make Riggedy Row better, I can go to this one, this allocation. But in doing so, I would harm Stankonia. So I can't make either player better without hurting another player. So this one is Pareto efficient. There's like a little shorthand that one of my students devised that I thought was pretty nifty, and I kind of teach it. And if you find it useful, you can do it. So if I were to line up the different outcomes, I'll do it down here. So if I were to line them up, negative 0.5, negative 0.5. Oh. Leave me alone, Excel. All right, 5, 20, 26, 5, 5. And I can use a shorthand. So I want to compare, you want to compare allocations to other allocations, basically. So I could compare negative 0.55 to negative 0.55, negative 0.5, negative 0.5 to 520, okay? So I would go allocation to allocation, and I would say, is there an increase? Is there a decrease? So if it's an increase, you have a plus. If there's a decrease, you have a minus. And if it's the same as 0, okay? So negative 0.5. Again, this is another one of those things where it's just easier on the board. Let me do this. So negative 0.5 to 5 comma 20. So I'm going to use the arrow to determine the point you're considering. So negative 0.5 to 520, you're increasing both payouts. So I put both as a plus plus. Okay. And the goal is if I can find, also if this makes no sense to you, don't do it this way. This is, a tip that I've learned that some students find helpful. Some students find it complete gibberish. So, if this isn't making sense, just ignore it. find the way that works for you. But if I can find a plus, plus, or plus 0, or 0, comma, plus, then the left allocation is not Pareto efficient. I should put allocation on the left. Okay. Okay, so what did I do? I saw that there was a double increase, basically. That's what I'm checking. So moving from negative 0.5 to negative 0.5, I saw that there's a double increase. So I can eliminate negative 0.5 from Pareto efficiency. I'm going to move this cell over so that we can keep doing it. Sorry. Guys, I missed the classroom. Okay. So we're looking for a plus plus, and if we can't find one in any of the other allocations, so if we can't find one comparing to each allocation, then we can say that the allocation on the left is Pareto efficient. So 520 going to 26 is equal to a plus minus, so I can't eliminate, plus minus can't elim. Okay, what about 520 to 55? Okay, that equals, you know what, the equal sign is probably confusing too. So I'm going to write is, and is, and I write so. So I'll use English. Is plus plus, so can elim. Oh, geez Louise. All right, so from 520 to 55, we have a plus minus. Okay, and what happens when you have a plus minus? You cannot elim. Can't elim, cannot eliminate. Okay. And then we can already, so once you eliminate something, once you know that it's not Pareto efficient, you don't have to consider that one anymore. So I'm going to cross this bad boy right out, strike through, so we don't even have to worry about it. Okay. And then we could do it. So we've done both of these guys. We compared this one to this one and this one. So I can say safely since I can't elim, no, and I've done all allocations, 520 is Pareto efficient. Ugh. There we go. All right, so this one is PE because You only have plus minuses. You don't have a plus plus, a 0 plus 0, or a 0 plus. Okay. So 0 plus means that one person stays the same, the other does better. Same thing with a plus 0, and a plus plus means both people do better. So if I can find one of those allocations versus the one I'm considering, the one on the left, then that means I can eliminate it. Okay. So what about 26 going to 520? So what do you have? You have minus is minus, plus, so can't elim. Let me make it a little small. There we go. I just want to get everything in here. Okay, so 26 to 520. So Stankonia loses. Okay, so you have a minus plus. Stankonia loses, Riggedy Row gains, so you have a minus plus, so you can't elim. What about 26 versus 5. That is minus, minus, so can't elim. So since I can't elim against both allocations, I've checked both allocations, 26 must be Pareto efficient. Okay, what about 5 to 520? So I have a 0, right? Stankonia doesn't lose, doesn't gain. And I have a plus, Riggedy Row gains, so can elim. Okay. You don't have to take it any further, but let's say I did want to take it further. So 26 is a plus plus, so can elim, not be. Okay, so you need to go kind of one by one, and once you eliminate something, you don't have to consider it anymore. You don't have to compare the other ones from it, but you just want to check: is there a party that gains? Is there an agent that gains while another agent doesn't lose? So is there an agent that gains while the other agent gains, or is there an agent that gains while the other player stays the same? The other agent stays the same. And if there is, then you can eliminate. And if not, you have to go to the next allocation until you've exhausted all the allocations, and then you can say it's Pareto efficient. Okay. Again, and if this way doesn't make any sense to you, you can just file it away in the things that you don't need to do. This is just like I said, this is just a helpful tool that that one of my students kind of developed as she was going through it, and she's like, oh, this actually makes a lot more sense this way. And I kind of liked it, so I thought, let's teach it as an alternative. The last point I want to make is, so notice we had a minus minus, or if you have a minus 0 or a 0 minus, a 0 minus going from here, from the left to the right, a 0 minus going from left to right is the same thing as a 0 plus going from right to left, right? So if you see a minus minus or a 0 minus or minus 0, it's the opposite. So you can, then the allocation on the right is not Pareto efficient, if that's easier for you. Otherwise, just go through it the normal steps like I just showed you. Okay. Okay. So a dove, you can make both players better off. Moving from hawk dove or dove hawk will necessarily, in order to make one player better off, you have to hurt another player. So these are the two Pareto efficient allocations: dove hawk and hawk dove. Okay.